Okay, we're given a piecewise function and we have to figure out if it's continuous or not. Let's review what continuity means. Continuity means that the limit of x going to a certain value of f of x is equal to the value at that point. So this is what it means to be continuous at x equal to c. Now, this left side is a limit, and the right side is the value. That in order to be able to say that these two are equal, a priori you need the left side to exist and the right side to exist. So if the left side fails to exist, for example, then it's automatically false that this equality is true, and therefore it's not continuous. Okay, or in other cases where the function value doesn't exist, there will be another case where it's not continuous. All right, let's do part A. Compute limit x going to 2 minus f of x. We had a few similar questions, so you probably recognize this. X squared minus 4. If x is less than 2, slightly less than 2, then this will be negative, right? Therefore, what would this evaluate to? It won't be x squared minus 4 because this will be negative. In order to make this positive, you need a minus in front. So in this case, when x is set to 2 minus, it will be negative of x squared minus 4 over x minus 2. So this above limit, this f of x, will be evaluated in this way. And I can factor the top, x minus 2 times x plus 2 divided by x minus 2. And then this will cancel, and now you can plug in 2 minus. This is 2 minus plus 2, and that's equal to 2 plus 2 is 4. 4. By the way, this minus here is not the sign of 2. This just means it's slightly less than 2. So this, you should think of this as like 1.999. Plus 2 gives you 4. So it'll be negative of 4. Okay, so that's the answer for part A. What about part B? Determine whether it is continuous at x equals to 2 or not. Whether this function f of x is continuous at x equals to 2 or not. Well, as I said, this left side has to exist, the right side has to exist, and they have to be equal. So let's see if the limit x going to 2 exists. Well, we already have the left limit. When does the limit exist? Well, it exists if the left and right limit both converge to the same thing. So we really need to evaluate the function when x is going to 2 plus. But if x is slightly bigger than 2, this will be just x squared minus 4 without the minus sign, because it's already positive. In this case, in the same reasoning as above, it factors, and you're sending x to 2 plus, and that will be positive 4. And since these are different, it's not equal, that means limit doesn't exist, and therefore it's not continuous. Suppose the limit of the function f of x goes to pi over 2, and all these f of 0 is 5, f of 2 is 3 pi over 4, and all these things are true. And there's this extra condition that the function is a strictly decreasing continuous function. This condition is just a technical condition that avoids some difficulties. So you don't really have to worry about this part too much. Okay, let's first do the limit of x going to 0 of f of x. Okay, where does f of x go to? It converges to pi over 2. So for this one, this part will converge to pi over 2. But where does g of x go when x goes to 0? This converges to 2. So that's going to converge to 3 times 2 minus 2, which is pi over 2 times 4, so it's 2 pi. How about this one? Well, sine of pi over 2 is 1. And because f of x, when x goes to 2, oh, this is a mistake. This should be really x going to 0. Okay. If x goes to 0, then this goes to pi over 2. So sine of pi over 2 minus sine of pi over 2, they will be both converging to 1. Right? So overall, this entire thing will converge to 0. Another way to think about this is, why not set t as sine of f of x minus sine of pi over 2. Then as x is sent to 0, because this converges to pi over 2, this entire thing becomes closer and closer to sine of pi over 2. And if you subtract the 2, you're going to get t also goes to 0. And therefore, we can rewrite this as limit of t going to 0 of g of t, because this entire thing is t, and we know that t goes to 0 as x goes to 0. And therefore, this is equal to g of t. When t is going to 0, it's equal to 2. Alright, actually, these additional values weren't used, and that's because f is not really evaluated at 0. You're evaluating f as x is getting closer and closer to 0. In that case, you get pi over 2. So in these limit ones, you shouldn't be using the value of the f. You should really be using the limit of f as x goes to 0. Okay, here's the graph of a function. Okay, find all values where f of x has a removable discontinuity. Removable discontinuity means if you can just plot one dot to make something continuous, that's called removable discontinuity. You can remove the discontinuity by plotting one dot. Okay, and the only case that you can have a removable discontinuity is when you have this open circle with two curves coming out from left and right. Okay, those are removable discontinuity, and people also call this open circle as R-pod, removable point of discontinuity. That's why this is called. So this is the only removable discontinuity. So x equal to 0 is the removable. Find all values where f of x has a jump discontinuity. These two discontinuities are jump because it goes from one place to another suddenly, right? So there's the value changes abruptly. So these two values, x equals to 2 and x equals to 7, has a jump discontinuity. Find all x values where fx is not differentiable. Well, any point that's not continuous, it's not differentiable. So anything that you wrote down as discontinuity should be included in here. In addition to that, any kind of corners that's present in the graph are points where it's not differentiable. So for example, right here, that's a sudden change in the slope, right? So this point will be a point where it's not differentiable. So we have to include that, which is x equals to 4. Now what is f of 7? Well, there are 3 circles at 7, but the one that's closed is this one, which has 1, which has the altitude of 1. So that's equal to 1. Evaluate x going to 2 plus of f of x. Okay, so here's 2. 2 plus means you're coming from the right. As you're coming from the right, the height is equal to 8. So this will be 8. Evaluate limit x going to 7. Well, if you come from the right, it'll be 3. If you come from the left, it'll be negative 4. But if you're just asking for the limit as x going to 7, we have to say it does not exist because the left limit and the right limit do not agree. Evaluate x going to 0 of f of x. Okay, if you're going towards to 0, as you can see, the left limit is 0 and the right limit also is 0, because the height at this point, the altitude at this point is 0. So in this case, the left and right limits do agree and the value is 0. Okay, evaluate f circle f6. What does this circle mean? It means composition of functions, which is like you plug in one function to the other. So f of 6 is plugged into the other one, f. And then f of 6 is what? F of 6 is 0, right? So you need f of 0. Oh, but what is f of 0? There's an open circle there. So in this case, it's undefined. So it was more like a trick question. Find the derivative. Okay, we have a bunch of derivative problems. Okay, so if I differentiate this, x differentiates to 1, and for this one we need to use the quotient rule. Differentiate the top times the bottom minus differentiate the bottom times the top, and that's 1 minus, because the derivative of constant is 0, that goes away. Minus minus is plus, and x minus 1 differentiates to 1, so 1 times 2 is what you have. That's what you have on the top. Now this is again another fraction, so you need to use the quotient rule. When you differentiate, it's top prime times the bottom minus bottom prime times the top over the bottom squared. S prime is 1. Square root of s differentiates to 1 over 2 square root of s, and 1 differentiates to 0, so that's what you get replacing this prime, and then you have s, and then you have square root of s plus 1 squared. Now let's try to simplify this further. This is square root of s plus 1. Now this is square root of s squared, right? S itself is square root of s squared. Why am I doing this? That's because if I write it that way, then one of the square roots will cancel, and you end up with 1/2 times square root of s. And that's great because now we have these two like terms which we can combine. So it will be 1/2 square root of s over square root of s plus 1 squared. So that's and then you can further simplify this by multiplying by the 2 top and bottom to just erase this and then have 2 in the denominator. Okay, so this is what you would get if you simplified. However, normally I would, for a lot of differentiation questions, I would just say do not simplify the derivative. In that case, you can just stop here and you don't have to simplify. There are cases where you do have to simplify the derivative in this form. That's the case when you have to find second or third or many different derivatives. Or in some cases, I ask you to find the slope at a certain point, or find the point of a given slope. In that case, you have to use the derivative to do some more algebra, so you have to simplify. Okay, the last one, this one is a product of two functions, so when you differentiate this, you need the derivative of the first one times the second one, plus the first is left as it is, and derivative of the second one, and that's e to the t cosine t minus e to the t sine t. Alright, another question with fractions, and you could use the quotient rule right away, but sometimes it's much easier if you simplify before you differentiate. So let's try to simplify this algebraically. So I multiply x minus 1 top and bottom. The reason I'm choosing to multiply x minus 1 top and bottom is because That way the denominators will be cancelled away. And that gives you x minus 1 minus 1. And this is x minus 1 plus 1. So it's x minus 2 over x. Alright. And it's a lot easier to differentiate this. Okay. Now, even better, you can write this as x over x minus 2 over x. X over x is 1, and 1 over x is x to the negative 1 power, right? So if you write it in this way, then you don't even have to use the quotient rule to differentiate. So now the derivative, we haven't differentiated yet, we still have to differentiate. If I differentiate this, constant goes away, and negative 1, by the power rule, negative 1 comes down, and you have to subtract 1 from negative 1, so negative 1 minus 1 is negative 2, so finally it's 2 times x to the negative 2. That's the final answer. You could write this in this format, 2 over x squared. Both are correct answers. Okay, this one, again, you can choose to just differentiate as it is, but it's probably better to simplify before you differentiate. So radical powers can be translated as fractional, radicals can be translated as fractional powers. So cube root of x squared is x to 2/3 power, and this is x to 1/3 plus 1/3 plus 2/3, that's 1. So that's what you have. You have to differentiate this. And 1/3 comes in front, subtract 1, that's 2/3, and derivative of x is 1. Okay. Again, you can further simplify this by rewriting this as a cube root, but let's not do that. Okay, this one is a simple application of the chain rule. The outside function is x to the 7th power, so if you differentiate this, 7 comes down, x squared plus 2, subtract 1 from 7, so that's 6, and the inside function has to be pulled out and differentiated, so that's 2x. How about this? Well, it's actually a really simple question. This is a constant multiple, that's a constant multiple, so you don't have to differentiate them. You can just pull it outside the derivative, and therefore you have a times 3x squared plus b times 1, so that's 3ax squared plus b. Another simple application of the product rule, u squared, if you differentiate this, u squared prime sine u plus u squared times sine u prime, that's 2u sine u plus u squared. Sine u differentiates to cosine u. This one you can apply the quotient rule, but I think I would like to have it simplified before doing anything more. So if I rewrite secant x as 1 over cosine, then it's a complex fraction, so I can multiply cosine x top and bottom to simplify. And that's cosine of x plus 1 over cosine of x minus 1. Okay, we still have to differentiate this. So if I were to differentiate this, it's a derivative of the top times the bottom minus derivative of the bottom times the top over bottom squared. So this is minus. Okay, and therefore cosine differentiates to negative sine and again here it's cosine differentiates to negative sine, so it's plus sine over the bottom squared. Okay, you can distribute this and you'll see some of these terms cancel. But let's not simplify algebraically. We'll just continue on. All right. For this one, you can rewrite this as 2 times 1 over sine x and minus cosine x over sine x. 1 over sine is cosecant x. Cosine over sine is cotangent of x. Therefore, if you differentiate this, that's just differentiating cosecant and cotangent. So it's negative 2 times cosecant of x, cotangent of x. That's the negative cosecant x, cotangent x is the derivative of the cosecant x. And derivative of the cotangent is negative cosecant squared x. So you're going to get positive cosecant squared of x. Alright, this one is chain rule. At some point you will need the chain rule, but a priori it's a quotient, so let's apply the quotient rule. So if you differentiate this, differentiate the top times the bottom, and then minus differentiate the bottom times the top over square the bottom. So it's 2 squared is 4, and then taking the square of 1 plus x squared square root. This square root will go away if you square it. So that's what you're going to see in the bottom. Right, this is e to the x. And square root differentiates to 1 over 2 square root. So instead of 1 over 2 squared of x, you have 1 plus x squared, so that goes in. But see, 1 plus x squared is the inside function, so at this point you have to use the chain rule. Inside function has to be pulled out and differentiated. If you differentiate 1 plus x squared, that's 2x. Okay. And that goes all over 1 plus x squared with times 4. Okay. And of course you can simplify further. There's even a complex fraction here, so you should really multiply this both top and bottom. But we're not going to do any simplification here. Okay. So this one, you can choose to differentiate it as it is. It's not too bad, but let me factor the square root of x out before differentiating. That's easier. That gives you e to the x minus 2x prime square root of x, then minus, no, actually plus, e to the x minus 2x is untouched, but you have to differentiate square root of x prime. E to the x differentiates to e to the x, 2x differentiates to 2, and square root of x differentiates to 1 over 2 radical x. Okay. Now, what does differentiating sine inverse of x give you? It's 1 over square root of 1 minus x squared. We need to use this over here. Square root of x differentiates to 1 over 2 radical x. By the way, I have to use the product rule, so I'm differentiating this first, leaving the second, plus leave the first, but differentiate the second. When you differentiate this, notice that instead of arcsine of x, you have arcsine of 2x. So you can apply this rule, but since 2x is the inside function, you have to apply the chain rule. So you have 1 over 2 radical x, arcsine of 2x, and then derivative of this thing is 1 over square root of 1 minus 2x squared. So instead of x, I'm writing down 2x, and then that 2x is pulled out and differentiated, so you will need an extra 2, because the derivative of 2x is 2, so that's what you're going to get. Okay. Alright, this one, this is a quotient, so let's apply the quotient rule. Differentiate this, multiply the bottom, minus, differentiate the bottom, multiply the top, divided by the bottom squared. 3 differentiates to 0, 5 to the x differentiates to 5 to the x, ln of 5, ln of x. Derivative of the log x is 1 over x, all over ln of x squared. Okay, derivative of the arctan, tan inverse function, is 1 over 1 plus x squared. So we have to use this. 1 over 1 plus x squared. Tan inverse of x. Okay. So if you differentiate this, you get 1 over 1 plus x cubed squared, and then this x cubed is the inside function, so that has to be pulled out, and you have to differentiate. That gives you 3x squared over 1 plus x to the 6th power. This time, you have a product of two functions, and then log of 5x is nested inside. So you will need both product rule and the chain rule. So apply the product rule. The derivative of this is equal to the first thing differentiated plus the first thing is untouched and the second thing is differentiated. Three x minus 1 differentiates to 3. And then this one, 1/2 power, 1/2, you should really rewrite this. Oh, we can use the fact that square root of x differentiates to 1 over 2 radical x. So if I apply that, this will be 1 over 2 times ln of 5x. But then since ln of 5x is nested inside, we have to pull that out and differentiate. And then you still see 5x inside as a inside function, so another chain rule is required. So when you differentiate this, is 1 over 5x times the derivative of this 5x, which is 5. Okay. If you differentiate this, let's see, this is 4 times e to the negative 3, and you can rewrite the next one as 5 times e to the negative of negative 3. You can flip, you can make the denominator go on top at the expense of negating the exponent. But if you negate the negative 3x, it's positive 3x. Okay. You get pi squared. So we're trying to differentiate this. And although these look very scary, remember these don't have any x's in there. What does that mean? If you notice these don't have any x's in there, that means these are constants. When you differentiate constants, they go away. Therefore, you have negative 5 times e to the 3x. 3 comes down, and you have negative 15 e to the 3x. So it has a very simple answer. Okay, this one is just a simple application of the chain rule. 1 over 2 times negative x squared plus 4x plus 5. and then you pull the inside out and differentiate. If you differentiate the inside function, it's negative 2x plus 4. Okay, if you differentiate this, cosine is an inside function. Sine differentiates to cosine. And this inside function has to be pulled out and differentiated. When you differentiate cosine ax plus b is again inside function, so first derivative of the cosine is negative sine, and the derivative of ax plus b is just simply a. Okay, so that's equal to negative a sine ax plus b times cosine of ax plus b. Okay, 3 differentiates to 0. And when you differentiate this, it's a product of two things. So it's 2x prime sine of 6 plus 2x e to the x plus 2x times sine of 6 plus 2x e to the x. And you see this 6 plus 2 times x e to the x is an inside function. So let's do that. 2 sine 6 plus 2x e to the x plus 2x. Sine differentiates to cosine. And this inside function has to be differentiated. So you pull this out and we differentiate. Now 2x e to the x, that's a product. 6 differentiates to 0. 2x times e to the x, you need the product rule. So that's going to be 2 sine 6 plus 2x e to the x plus 2x cosine 6 plus 2x e to the x. And when you apply the product rule, 2x differentiates to 2 plus 2x, and e to the x differentiates to e to the x. That's what you get. Alright, this time they're both chain rules, but it's somewhat different. Here, log of t is the inside function. There, t squared is the inside function. Okay, so here you have to differentiate as if you're differentiating x squared. So 2 comes down, ln of t, and then ln of t being the inside function has to be pulled out and differentiated. And ln of t squared, it's 1 over t squared, and t squared, which is the inside function, has to be pulled out and differentiated. Okay, ln of t is 1 over t, so you have 2 over t ln of t. And this is 2t over t squared, so t and t squared cancels, and you get 2 over t. Okay, 5 to the x differentiates to 5 to the x ln of 5. And you can really think of e to the x cosine 2x, this entire thing as the inside function. And therefore, when you differentiate this rule says you're going to get 5 e to the x cosine 2x ln of 5, but this inside function has to be pulled out, and you have to differentiate it by the chain rule. Okay, now this is a product of two functions. That means you have to use the product rule. E to the x differentiates to e to the x. Cosine 2x is left as it is. And then e to the x, I don't do anything. If you differentiate cosine 2x, that's negative sine 2x. And then 2x is the inside function that has to be pulled out and differentiated. Okay, so probably this. Okay. All right. Cosecant. What about the cosecant? Derivative of the cosecant of x is negative cosecant x cotangent of x. And because instead of this x you have x squared plus 3, when you differentiate it, you're going to get negative cosecant, let me erase that, negative cosecant of not x, it should be x squared plus 3. Same thing here, cotangent of x squared plus 3. And then that inside function has to be pulled out and you have to differentiate it. And that differentiates to 2x, so let me put here 2x, negative 2x cosecant of x squared plus 3, cotangent of x squared plus 3. Okay, what is f composed with f? And we have to find its domain. F composed with f simply means f, and you're inserting f of x into the function f. It's a function composition. And because this f of x is square root of 4 minus x, this is what you're trying to get at. Now, what is f of square root of 4 minus x? It's good to use two-step procedure in determining what this is. First, we're going to copy this definition down. F is what? It's square root of 4 minus. And although I said copy, I really didn't copy it. What did I do? Every time I see an x there, I put parentheses. Okay. Why would I do that? That's because if I want f of square root of 4 minus x, I need to place that inside this parenthesis. And that means I have to put the same thing inside all the parentheses I create. So that's what you get, okay? That is the composition of two functions. Now, what is the domain of this function? Okay, that's going to be interesting. First of all, I can't have 4 minus x as negative. It has to be non-negative, right? This thing can't be negative. So that means x should be less or equal to 4. Okay, so x can be 0, 1, 2, 3, 4, and those are okay. What about negatives? Is this okay? Well, negative 1 still satisfies this inequality, and you can go on actually quite a while. You can do negative 4, negative 5, negative 7, negative 11. But at some point, you're worried because this thing here might become negative. When does this thing become negative? That's when this thing becomes 4. When this is equals to 4, then 4 minus 4 will become 0, and that's okay. But if it's bigger than 4, then you have a problem, right? So when does this become 4? Well, this thing becomes 4 when 4 minus x is equals to 16. If this thing is 16, square root of 16 will be 4. And solving for x, you get x equals to negative 12, right? 4 minus negative 12 is positive 16. So when x is negative 12, this entire thing becomes 0, and then square root of 0 is okay. But if x is less than negative 12, then you're in trouble. So for example, if you have x equals to negative 13, then this thing inside is square root of 17, and then this becomes negative, and you're in trouble. So you end up with this extra condition that x should be less than or equal to 4, but it still should be bigger or equal to negative 12. That's the domain. In terms of interval notation, the domain is from negative 12 until 4. Okay, now the next question is, what's the derivative of this function? Okay, you have something complex inside the function, so that means I have to use the chain rule. 1 over 2 times square root of 4 minus square root of 4 minus x. And the chain rule says, take the inside thing, pull it out, and differentiate. Which differentiates to 4 differentiates to 0, so that goes away, but this thing is 1 over 2 times square root of 4 minus x, and then this is, let me erase this and draw again. It's 4 minus x there, but then 4 minus x is again nested, so you have to pull it outside and differentiate. What's the derivative of 4 minus x? It's negative 1, isn't it? So that's what you have. You don't have to simplify unless you're going to use it for the next one. So let's just leave it at that. Okay, number 17. Here is the value of g of 4, which is equal to 3. G prime of 4 is 5. And f of x is gx over x. And the questions are, what's f prime of 4? And another question is, what's square root of f of x? Differentiate and you plug in 4. Okay, first question. To do f prime of 4, I have to differentiate g of x over x, and then after differentiating, I have to plug in 4. Now this is the quotient, therefore I have to use the quotient rule, differentiate the top, times the bottom, minus differentiate the bottom, times the top, and divide it by the bottom squared. And I have to plug in 4 into x. That gives you g prime of 4 times 4 minus g of 4 over 16. Then I can plug in these values I'm given. G of 4 is 3, g prime of 4 is 5, 5 times 4 is 20, g of 4 is 3 over 16, so it's 17 over 16. Now part B, I have to differentiate f of x, and I have to plug in x equals to 4. Alright, this one is a nested function. F of x is nested inside the square root, so I have to use a chain rule. 1 over 2 square root f of x you have to pull out and differentiate. And then I have to plug in 4. So I get 1 over 2 times square root of f of 4 times f prime of 4. Okay, what is f of 4? F of 4 is, well, let's see. Let's figure out from here. F of 4 is g of 4 over 4. And g of 4 is 3, so it's 3 over 4. So f of 4 is 3 over 4. Okay. And f prime of 4, already I have it here, right? F prime of 4 is 17 over 16. Okay, 2 can go inside as 4, and it will cancel with the 4 in the denominator. So the first one will actually simplify to 1 over square root of 3 times 17 over 16, and because you have the square root in the denominator, you should rationalize. So you multiply square root of 3 top and bottom, and you get square root of 3 over 3 times 17 over 16, which can be written again as 48 as the denominator, and 17 times square root of 3 as the numerator. Compute the 4 derivatives of this function. Okay, if you were to differentiate it as it is, you would be using the product rule, but that's not so pleasant. So let's try to simplify before we differentiate. Okay, you can FOIL. You can FOIL these two multiplied, all that. It's a little confusing, so let me just not write these. Let me just say it while just pointing. 2x times x cubed, so it's 2x to the 4th. 2x times 1. Negative 1 over x squared times x cubed, that's just minus x. And then this times this is negative 1 over x squared. Now these are like terms, therefore I can simplify that as just x. And this one, since I have to apply the power rule to differentiate, I might as well change that into exponents. So that's x to the negative 2. Now this is much easier to differentiate. What's the first derivative? That's 8x cubed plus 1 minus negative 2 comes down to make it plus 2, and subtracting 1 from negative 2 gives you negative 3. Have double prime of x, 3 comes down, times 8 is 24 x squared. Constants just disappear. Negative 3 comes down to give you negative 6. Subtracting 1, you get that. Have triple prime of x is 48x. 4 times, oh, sorry, this is negative 4. Negative 4 times negative 6 is positive 24. And negative 4 minus 1 is negative 5. And then finally, the fourth derivative. Sometimes if you have too many derivative signs, then you can just instead use parentheses with that number. So if you differentiate 4 times, that's 48. Negative 5 gets multiplied to 24, that's negative 120. And subtracting 1 gives you negative 6. So those are the first 4 derivatives. Okay. Now ddx is just a Leibniz notation for derivatives, so this just means you're differentiating. 3 comes down to give you 9x squared. This one, you can use the quotient rule, but you should really think of this as 2 times x to the negative 2. So negative 2 comes down and makes it positive. 2 times 2, that's 4. X to the negative 3. You already know what's the derivative of square root of x. And this one is just a constant. That's also constant, so those are zeros. So you end up with 9x squared plus 4x to the negative 3. 2 cancels and you get 1 over square root of x. Now here we have 2 derivatives of this function. And you have to do one by one. First, since it's a product, we have to apply the product rule. Let me leave another prime here because we have to do another prime after this. It's the second derivative. This I'm only taking one derivative. Derivative of x plus 1 is just 1. Derivative of square root of x is 1 over 2 square root of x. And I still have to differentiate. Okay, and this time I really want to simplify before I differentiate. If you're doing multiple derivatives of one function, it's good to simplify before you do the next one, because it can get really messy. So I'm going to multiply square root of x top and bottom, and actually multiply 2 top and bottom so that I have common denominators. That way I can have just one single fraction rather than 2. That's much simplified. Square root of x times square root of x is square root of x squared, which is just x, and 2 is multiplied to it, so it's 2x. And on this side, there's x plus 1. So this is 3x plus 1 over 2x, and that's what you're supposed to differentiate. Oh, sorry. This is 2 square root of x. Okay, and then you have to use the quotient rule. 3x plus 1 prime, 2 radical x minus 2 radical x prime, 3x plus 1 over the bottom square, so it's 4x. If you square 2, it's 4. Square root of x squares 2x, which is 3 times 2 is 6, so 6 square root of x. And then this one is 1 over square root of x times 3x plus 1 over 4x. Okay, let's not simplify it further. This time I'm asked to find the derivative and evaluate at pi over 3. So let's try that. F prime of x is 2 cosine of x. Tangent differentiates to secant squared. And therefore f prime of pi over 3 is 2 times cosine pi over 3 minus secant is 1 over cosine, so it's 1 over cosine squared pi over 3. Okay, what's cosine pi over 3? It's 1/2. So 1/2 times 2 is 1. Minus 1 over 1/2 squared is 1/4. And you can use keep, change, flip, or just simplify this. It gives you 4. So 1 minus 4 gives you -3 as the answer. Now this one looks like a quotient rule, but if you think for a moment, secant is 1 over cosine, right? So this is really 3x squared minus 6x times 3x squared minus 6x times cosine of x. And that's a lot easier because product rule is easier to apply than the quotient rule. Now I'm going to use product rule, product of two functions. Okay, 3x squared minus 6x, and then cosine x prime 6x. Okay, and then 6x minus 6 cosine x, 3x squared minus 6x, cosine x differentiates to negative sine of x. Okay, so final answer is 6x minus 6 cosine x plus 3x squared minus 6x times negative sine x. Alright, we have to differentiate 2x cubed e to the x minus x prime. This part is a product. X differentiates to 1. Okay, so maybe I should say that if you have a bunch of terms, you can differentiate individual terms. Constants can be pulled out. So you can do this. And then you can apply, here you have to use the product rule because it's a product of two things. So differentiating the first one gives you 3x squared times the second. Leave the first and differentiate the second. E to the x differentiates to e to the x, so that's nothing different. If you differentiate x, it's 1. Okay, here is omega equals the square root of k over m, and because you have d omega over dk, you're thinking of this as a you're thinking of this side as a function of k where m is a constant. Alright, what does that mean? Well, if you're trying to differentiate square root of k over m, and then you can think of this as square root of k over square root of m. This square root of m in the denominator is just because m is a constant, square root of m is also a constant. And if you rewrite it as 1 over square root of m, this is a constant, times square root of k, a constant multiple can be pulled out. And you're only differentiating square root of k, where k is like the x. So if you know how to differentiate square root of x, it's almost the same thing. So we differentiate square root of x as 1 over 2 square root of x. So instead of x, we have k. So let's write down k. And therefore, what you have is 1 over 2 times square root of mk. Now, if this is confusing, I have a suggestion. Why not just, instead of 3, instead of m, just put something like 3 in here and see if you can differentiate. If you can differentiate square root of x over 3, if this is okay for you, then differentiating this won't be that hard. Just try this one first and pretend this m is like 3 and just follow the exact same steps and you're going to get the same answer. This is about second derivative, so let's find the first derivative. It's a product of t and cosine 3t, so we should be using the product rule. T differentiates to 1, so it's cosine 3t, whereas cosine 3t differentiates to negative sine 3t. And since 3t is nested inside, you have to use the chain rule. 3t comes out, and you differentiate 3t to give you 3. And therefore, it's cosine 3t minus 3t sine 3t. Now, what is h double prime of t? That's, you differentiate the first one, cosine differentiates to negative sine. Pull the 3t out and differentiate, it's 3. Okay, and then this one, you need the product rule. So let's write down 3t prime sine 3t, okay, plus 3t times sine 3t prime. That's negative 3 sine 3t, and then minus 3 sine 3t minus 3t. Okay, this is sine differentiates to cosine 3t. 3 comes out because of the chain rule. And because the question said simplify your answer, we really need to simplify. These two are like terms, so negative 3 plus negative 3 is negative 6 sine 3t. 3 times 3 is 9, so it's minus 9t cosine 3t. If you have arc sine, what's the second derivative? First derivative is 1 over square root of 1 minus x squared. Sorry about that. Let me. There's some trouble with graphics at this point. Okay. So the derivative of arc sine is 1 over 1 minus x squared. And when you differentiate this again, oh, you have two options. You can just differentiate as it is. Then you will need to use the quotient rule. But a lot of times, if you do many derivative questions, you will notice that a lot of times chain rule is much better to use than trying to use the quotient rule. So let's write it like this. Square root is 1/2 power, but because it's the reciprocal of this, you can put a minus. So this is same as, this thing is same as 1 minus x squared with the negative 1/2 power. Once you put it in that form, then what's f double prime of x? F double prime of x is negative 1/2 comes out, and 1 minus x squared, you subtract 1 from negative 1/2, so it's negative 3 over 2. So that gives you negative 1/2 times minus is 1 over, and 1/2 power is square root, and 1 minus x squared. This is the third power. And you can finally simplify it as negative 1 over 2 times square root of 1 minus x squared, so cubed. For each function, find the 5th derivative and then find the 97th derivative. Okay, let's try f prime of x first. You need to use the product rule. X prime e to the negative x, then plus x times e to the negative x prime. This is just 1. And e to the negative x differentiates to e to the negative x, but because of the chain rule, you have to multiply by the derivative of the inside function, which is -1. And since both of the terms have e to the negative x as a factor, let's factor it out, and you get 1. And this is x times -1, so it says 1 minus x. Okay. Let's find the second derivative. Again, you have to use the chain rule. Plus this differentiates to negative e to the negative x. This differentiates to -1. Since they both have e to the negative x, it's -1 plus x and then -1, so it's e to the negative x, x minus 2. Okay, are we already finding a pattern? If you're already finding a pattern, that's wonderful. If you're not, let's just do one more, and probably that's enough. F triple prime of x, we're differentiating this one. So e to the negative x prime, x minus 2, plus e to the negative x, x minus 2 prime. Negative e to the negative x, by the chain rule, will have this minus attached. And this differentiates to 1. So you end up with, if you factor the e to the negative x out, then negative x plus 2 plus 1. So you end up with e to the negative x, negative x plus 3. Okay, so we have the 3 derivatives. And I guess a good way to see what's going on is maybe see that these negative x's have a minus in front, whereas this one doesn't. So why not rewrite this as minus e to the negative x, x minus 1. Okay, so if you multiply the negative inside, you'll see that these are the same thing. Same thing over here. Why not rewrite it as negative e to the negative x, x minus 3. Then it follows a wonderful pattern because it's x minus 1, x minus 2, x minus 3. It says 1, 2, 3. So if you differentiate 5 times, it will be x minus 5, right? Another thing to think about is if it's even, it's positive. If it's odd, 1 or 3, it's negative. So we see that the answer is f differentiated 5 times of x will be negative because you differentiated odd times, and e to the negative x, and it will be x minus 5. And also f differentiated 97 times will be, because again this is odd, you need a minus, and x minus 97. That will be the answer for f of x. Now let's move on to g. If you differentiate g once, the chain rule says this inside function has to be pulled out and differentiated, and you get 2 times e to 2x. Another prime will give you, if you differentiate twice, again by the chain rule, you will have to multiply the derivative of 2x, which is 2. So in other words, every time you differentiate, a factor of 2 will appear. So we choose square root e to the 2x. And that's actually a lot easier than the first one. If you differentiate 5 times, what would you get? It would be 2 to the 5th power of e to the 2x. And if you differentiate it 97 times, then it will be 2 to the 97th power e to the 2x. Okay, now sine 3x. Again, because of the chain rule, if you differentiate through, it will pop out. However, sine differentiates to cosine, right? So cosine 3x, and then inside function comes out, and you have to differentiate, which creates 3. So that's your first derivative, 3 times cosine 3x. Second derivative is cosine differentiates to negative sine, and because another 3 comes out from the chain rule, you have 3 squared negative sine 3x. Third derivative, sine differentiates to cosine, positive cosine, another 3 appears. Okay, I think this is complicated enough that maybe for the 5th power we'll just differentiate that much. Okay, 3 to the 4th. Cosine differentiates to negative sine, which is positive sine. And 5th power, 5th derivative, not power, 5th derivative is 3 to the 5th power cosine of 3x. Now let's look at the pattern here. It starts from positive cosine, negative cosine, positive sine, positive cosine. Right, and then this 3 to the power, we don't have to worry about that too much because it just goes like 1, 2, 3, 4, 5. So we know that h to the 97th power will be 3 to the 97 and sine or cosine something 3x with a minus or plus. So that's what we have to know. Another thing that we notice is that if you differentiate even number of times, it's going to be sine. Odd number of times it's going to be cosine. So we know that this one, since 97 is odd, it should be cosine 3x. Now what's left is whether this will be positive or negative. Okay. When do you get positive sine? Well, if you don't differentiate at all, it's positive sine. If you differentiate 4 times, it's again positive sine. And because if you differentiate sine 4 times, you come back to sine, right? Sine differentiates to cosine, cosine differentiates to negative sine differentiates to negative cosine, and then when you differentiate negative cosine, you come back to sine. So if you take sine or cosine and differentiate it 4 times, you end up with the positive of the same thing, okay? The same thing. So we actually know what's going to be when you differentiate 96 times, because 96 is divisible by 4. The one right before this should have been positive sine 3x. And if you differentiate positive sine 3x, are you going to get negative cosine or positive cosine? It will be positive cosine, right? So the answer is this positive 3 to the 97 cosine 3x. That's how you get it. Draw the graph of the derivative for the given function's graph. Okay, so for these smooth varying curves, the first thing you want to know is when does it have a horizontal tangent? Here's one, here's one. And in terms of the derivative, those are the places where the derivative is equal to 0, because the horizontal tangent means 0 as a derivative. So at -2, the derivative should be 0. At 2, the derivative should be 0. Okay. Now, between -2 and 2, because the graph is decreasing, look at the slopes. What's happening to the slope? The slopes are all negative, right? So between -2 and 2, the slope will be negative. And because it's just a sketch, you don't really have to know how much. I mean, if you were really careful, maybe this is more like slope right here is more like -1/2. But I wouldn't worry about it too much. So you have this. And then afterwards, it's going up. So the the slope is positive and it's going increasing and increasing, so positive. Over here the slope is also positive, so it's positive. Okay, so that's the graph of the derivative. It should be something like this. Okay. You should note, write down here that at -2 and 2 the derivative is equal to 0. What about this derivative? Well, what's the slope here? 0, right? So from -4 to -2, so until -2, the slope will be 0. Now what's the slope here? Well, if you do rise over run, rise is -2 and run is 1, so -2 and 1. So rise over run gives you -2. So the slope of this line here is -2 and it's not changing. So if you drew the tangent line as you're going here, it's all the same line. It's this line, and the slope is always -2. So I can say here's -2, and this, it maintains this -2. Okay. All right, from 1 to 3, what about 1 to 3? Here, if you do rise over run, it's rise is 1, run is 1, so it's 1 over 1. So the slope of this portion is 1, and it's not changing. So if this is 1, it's like this. And then afterwards, the rise is -3 and run is 1, so -3 over 1 is -3. So the slope over here is -3. So here's -3. And that's the graph. So it's this, 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 this. Those are four horizontal lines. What about at exactly these locations? What should I do? Well, what's the derivative at these points where there's a sharp turn? The derivative does not exist because it's not differentiable. So what does that mean? If the value doesn't exist, you have to put an open circle there. So that is the derivative. Okay, suppose we have two differential functions, fx and gx, given that f of 3 is 3. If these are given, what is f gx at x equal to 2? Well, this is a simple application of the chain rule. What is the derivative? It's f prime of g of x times g prime of x, right? That's the chain rule. And because we have to evaluate it at x equal to 2, we have to put 2 in here. And then we evaluate. G prime of 2 is what? G prime of 2 is -1. G of 2 is 3. Okay. And when I replace G of 2 by 3 and G prime of 2 by -1, I end up with f prime of 3 times -1. And what's f prime of 3? That's -2. So it's -2 times -1, -2 times -1, which is +2. Okay, what about this one? This is another application of the chain rule. 3 comes down, f of x squared times f prime of x, but you have to evaluate it at x equals to 3, so let's replace x by 3. And we can now use that f of 3 is 3. F prime of 3 is -2. So that's -54.